Okay, so good afternoon, students. Welcome to Rapid Revision Series NEET. So today we are going to discuss current electricity, and we are going to discuss that is lecture number 9. So hope you are very well and you are doing good number of question solving. And this revision time, so mostly the formula part revision you have to do, and some key concept which are written so far in that. So this chapter which we are going to discuss today is a little bit lengthy chapter, but this is weightage chapter and as we can see the weightage wise, if you see this will be, we are having how many questions that we can expect from this. So we can expect 2 to 3 questions on an year. So last year if we talk about the 2024, so 3 question has been asked from this, and again 2 questions was there in re-examination. So on an every year 2 to 3 questions we can expect from this current electricity. Single year there was some 4 questions where have been asked, also has been asked. So 3 to 4 questions that we can expect from this. So let's start today's journey. And what are the things that we are going to discuss? Ohm's law, Kirchhoff's law, cells EMF, internal resistance. Next we have electrical energy and power, and electrical measuring instruments. So these are the topics that chapter is divided in these further topics, which will be going to discuss one by one. So first one is, if we talk about the electric current. So what is electric current? Electric current is the rate of flow of the charge. So electric current, 2 types of current is there. Average current. What is average current? So we'll be writing this delta Q by delta T. So that is average current. Second is instantaneous current. So instantaneous current is given by dq by dt. So this will be instantaneous current, dq by dt. So whenever over the time interval we are calculating the current, that is we define for the average current over one particular time. When the charge is given as a function of time, and that we'll be writing this differentiation of this. From here we'll be calculating the instantaneous current value. So here if the charge is given as q is equals to 5t square plus 3t plus 2. So in this case, from here if you differentiate this, I equals to dq by dt. So this will give us the instantaneous value at one particular time. Instantaneous value of the current at one particular time, that is I equals to dq by dt. This is the average current and instantaneous current. Certain terms that we are going to discuss in this. What is that? First is, if the conductor is having length L and current is flowing through the conductor is I. Okay, current that is flowing through conductor is I. The first one that we define current density. So when we define the current density is defined as J is equals to I divided by area. Or in terms of this we can write here J dot A is equals to I. Assuming that current density is constant throughout this, so J dot A equals to I. If you write in just scalar form, current density is given by I divided by area A. So J is equals to I by A. So where I is the current that is flowing and A is the area. A is the area of the cross section, I will be current that is flowing over here. A is the area of the cross section. So this current density is I divided by area. Second thing that we can discuss from here is that drift velocity. So what actually happens that whenever in given conductor, whenever electric field is in given conductor, so many number of electrons will be there. In absence of electric field, they will be moving randomly with each other. In presence of electric field, if we give some battery or something, what will happen? They will be aligned, they will be drifted in the direction of opposite direction of electric field. So if all the electrons are drifted in opposite direction of electric field, this gives rise of electric current. So here we define drift velocity. So drift velocity, for example, the drift velocity is given by E, capital E, tau by m. This is drift velocity we have. What is capital E here? Electric field. And what is tau here? Relaxation time. M is the mass, E is the charge of the electron. So this is the drift velocity that we have, and this in terms of the vector form it will be minus will be getting. So if it relation between the current and drift velocity that we get here, the relation between current and drift velocity, that we can write here I is equals to N E A V D. Now what is N here? Number of electrons per unit volume for the given conductor. Mostly for the conductors, this having this much number of electrons, 10 to the power 28 per meter cube of electrons. For this, drift velocity is the order of 10 to the power minus 4 meter per second. So this is the velocity with the electrons get drifted opposite direction of electric field because of this electric field that we are applying. So this I equals to NEAVD. So if you talk about this J, what is J? I divided by area. So this side NEAVD divided by area common. So J is equals to NEVD. So both are in the vector form over here. There is J equals to NEVD. So this is the current density I J divided by I divided by area. Next we have this. If we talk about this particular term, that is tau, relaxation time, and this is mass. The tau is the time between two successive collisions. The time between two successive collisions will define as tau. Next we define in this case, that is the Ohm's law. So what is Ohm's law? For a given this conductor, so if we have this, if you are applying the potential difference voltage V and length of the conductor is L, in that case what we define, potential difference V is equals to I into R. And how we get this V equals to I into R? That is, we can write here V is proportional to I, and what is R here? R is the resistance, that is the obstruction offered to the flow of the current in the given piece. So R equals to, we can also write here V by I. And what is R? R we write in terms of this rho L by A. What is rho? Rho is the resistivity. And what is formula of rho? Rho is given by M by N square tau. How we are getting? I am not deriving because we don't have that much time to go for each and every formula derivation. We don't have that much time. So what is resistance? We'll be writing this. Resistance is given by R equals to rho L by A. So this is also one formula. So R equals to rho. What is rho? M by N square tau into L divided by A. R equals to rho L by A, where L is the length of the conductor and A is the area of the cross section of the conductor. A will be area of the cross section of the conductor. That's it. M is the mass of the electron, E is the charge of the electron, N is the number of electrons per unit volume. Just now I told what is the value, that is 10 to the power 28 per meter cube, right? So moving to next particular part of this, we know V is equals to I into R. This is the scalar form of the Ohm's law we can write. Corresponding, we write here electric field E is equals to I. I you just replace by current density, okay? I replaced by current density J. Resistance you replace by resistivity rho. So this we are getting this particular relation E is equals to J multiplied by rho. Or I can write this side, what is J in terms of this E divided by rho. What is 1 by rho? Conductivity, okay? So J is equals to sigma times of E, that is conductivity. Sigma is the conductivity, and what is sigma? Conductivity, that is 1 by rho, resistivity, or rho is 1 by sigma. So these are the formulas that we should have, we should keep in mind while solving the problems from here, because some of the questions have been asked from these formulas as well. So let's discuss this. Temperature dependence of the resistance. So what happens? The solids which have the negative temperature coefficient of resistance is given by. So there are insulators, there are metals, and there are semiconductors. So on increasing the temperature, remember this, for metals, especially for metals, I am telling, for metals, temperature increases. What happens? Resistance also increases. Resistance depends on R is equals to M. Resistance depends on, that is resistance ml divided by N square tau into A. So on increases in temperature, what happens is that collision between the electrons increases. Collision increases means tau value will decrease. Tau value will decrease means resistance value will increase. So this happens during increase in temperature. Resistance increases. Resistivity also increases. So for metals, temperature increases, resistivity increases. And what is the formula here? R equals to R at T is equals to R naught into 1 plus alpha T minus T naught. This is alpha is the temperature coefficient of resistance. If alpha is positive means with increase in temperature, this resistance will also increase. This is for only metals. So alpha is positive for metals, but for non-metals and for this insulator and semiconductor. For semiconductor especially, temperature increases. What happens? Temperature increases, resistance decreases, as well as resistivity decreases. Keep these things in mind. And because of this, alpha value will be negative. If alpha is negative, then it will decrease. For insulators also, it will decreases. Temperature increases, this will decrease, alpha value is negative. So answer is option C for insulator and this. Right. Next we have a question from the drift velocity. Across a metallic conductor of non-uniform cross section, a constant potential difference is applied. The quantity which remains constant along the conductor will be given by. So this very good question over here. So here we have a uniform cross section metallic conductor here we have, and we are applying connecting to the battery like this, having the potential difference V. So in that case, what they are asking? Constant potential difference. The quantity which remains constant along the conductor is given by. The quantity which remains the constant along the conductor. First thing is that current remains same. Whatever the current, what is current? Rate of flow of the charge. So whatever the charge that is flowing across this cross section, the same charge will be flowing across this cross section, across this cross section. All the cross sections, same charge will be flowing. The current remains same across that. Remember this. So current will be same. What is current? I. So current will be same. If I take A, if I take B. So current at A is equal to current at B. I think no doubt in this. Current will remain same. Answer is option D. Current will remain same. Then what will change? Current density should change. What is current density? I divided by area. Where the area is more, here the area is less. Here current density should be more. So J is inversely proportional to area. So J at A should be more than J at B. Remember this. Next we have drip velocity. What is I? What is J? What is J? NEVD. So J is directly proportional to VD in inversely proportional to area. So again from here, drip velocity at A will be more than drip velocity at B. Next we have electric field. What is electric field? Magnitude we can get from here E capital E tau divided by M. So from here we can write VD is directly proportional to electric field. So from here I can write electric field at A is more than electric field at B. So these are the pointers that you should keep in mind. Current density, electric field as well as drip velocity will be more near at point, which point? Where having less area of the cross section is there, but current will be same. Again, let's talk about this particular question where uniform wire of diameter D carries a current of 100 milliampere when the main drip velocity of electron in the wire is V. For a wire of diameter D by 2 of the same material to carry a current of 200 milliampere, the mean drip velocity of electron in the wire should be given by. So here I is equal to NEA VD. NEA VD. Right? Yes. I equals to NEA VD. That this particular formula that we are using over here, I is equals to NEA VD. Now, so uniform initially diameter is D. Initially diameter is D, and current value is this much. Okay. So initially diameter is D. Carries a current of 100 milliampere when the mean drop velocity of electron is V. For a wire of diameter D by 2 of the same material to carry a current of 200 milliampere of the same material. So as the material is same, remember this. N value is defined for a given material. Once the copper material is fixed, copper N value will be fixed. E is the charge of electron, that is fixed. So VD depends on two things. What is that? VD depends on two things. What is that? Current as well as area. I divided by NEA. So VD is proportional to I divided by area. That's it. VD is proportional to I divided by area. So drip velocity V is proportional to I divided by area. What is area of the cross section? Pi d square. So remember this. So V is proportional to I by d square. That's it. So let's solve this particular question over here. So I'll be writing this case 1, this is case 2. I'll be writing this V2 by V1 as the V is proportional to what? I divided by d square. So this will be I2 by I1 into d1 by d2 ka whole square. So solving this, what is I2 value? So what is I2 value? 200 milliampere. And what is I1? So 200 divided by 100 into d1 by d2. So what is d1 value? D. And what is d2 value? D by 2. Square we have to do. So this one is 1 and this one is 2. This is 2, 4. So this will become how many times? 8 times. So answer is 8 into V. Clear? I hope all of you got this one. Answer will be 8 into V. Next, this particular question over here. Column 1 gives the certain physical quantities associated terms with the flow of the current through a metallic conductor. Column 2 gives the same mathematical relation between them. So here, drip velocity. What is formula of drip velocity that we have to? Just now we saw drip velocity. So drip velocity E capital E tau divided by M. This is the formula of drip velocity. So A is R. From here directly we can say A is R. Let's check how many of them is having A is equal to R. Okay, 1, 2, 3, 4. All options are having A into R. Okay, fine. Let's talk about the current density. So what is current density? So D. Current density J. What is J? NEVD. So D is having Q. D is having Q. Let's check how many D is having Q. So this one is eliminated now, and this one is also eliminated because D is having Q. This one is having Q. Let's talk about the C. What is that? Relaxation period. So electrical resistivity. Just now we saw J. Just now we saw that. What is J? E by rho. So what is J is equal to E by rho. What is rho? E by J. Okay. So this. So rho is equal to E by J. So this particular case, that is electrical resistivity is Bs. B1 is having S. So which option is there? Which option is there? Option B. A ka R, B ka S, C ka P, D ka Q. So this is how we solve this relation between different physical quantities in current electricity. So moving to next, that is Ohm's law we discussed, V is proportional to IR. Kirchhoff's law, Kirchhoff's current law will be having, and second is Kirchhoff's voltage law. So if we have, let's say this is one resistance, and let's say this is one resistance, and this one is also one resistance, and this is also one resistance over here. Let's say current is coming here I1, and from here current is coming I2, from here current is going I3, and from here current is going again I3. So at this particular junction, what is the incoming current here? I can write here I1 plus I1 is incoming plus this side I2 is also incoming, and this side which is outgoing, which is going out from this particular point. This is going this way, this is going this way. This will be I3 plus I4. At one particular junction, no net incoming current should be equal to net outgoing current, because wire is not hitting the charge. That is fundamental of conservation of the charge. Wire is not consuming any charge. Whatever the charge that is flowing at this particular point has to go out. Wire is not consuming any charge. So this is what Kirchhoff's first law. KCL we also got. Kirchhoff's current law. Second is KVL. What is KVL? The summation of the potential drop across the closed loop will be zero. Across the closed loop will be, again I am using the word across the closed loop will be zero. Summation of the potential drop across the closed loop will be zero. And there is some kind of, in this case, there is some kind of the rules that we have to follow when we are applying this Kirchhoff's law. So for example, across the resistor if I write, across the resistor if I go, and this side if I go across the battery, suppose if I go, so across the resistor, suppose if I am going this side, so this one is I, resistance is R. If I am going from A to B, okay, across the battery, suppose if I am going, let's say from A to B I am going, doesn't matter in which direction of current I am moving, but for the resistor, suppose if I am moving across in the direction of the current, then delta V I will be writing here minus I into R. And here again delta V will be writing here minus E. What is E? E is the EMF of the battery if you are moving from positive of the battery to negative of the battery. Second case, reverse case, suppose current is flowing this way only, current is flowing opposite, okay, current is flowing opposite, right? But we are moving from A to B, opposite to direction of current. So in this case, what we will be writing here? Delta V. So what is delta V? Plus I into R. And in this side, when we are moving from this point to this point, we are moving in the direction of negative to positive, so delta V equals to plus E. So these are the convention that we have to take while solving the problem from the Kirchhoff's law. So this is what Kirchhoff's voltage law. This is conservation of energy talks about. So we'll be discussing this, some of the questions based on this, okay? Right. So combination of the resistor if you have. So if you combine the resistors, first one is series combination. So series combination, always remember that if you have series combination, resistance R1, after that one more resistance R2 is there, and here one more resistance R3 is there. It is connected to the combination like this. So here resistance R1, R2 and R3. So what actually happens, that first point that you should keep in mind, current remains same. Remember this, current remains same across each resistance in series combination. Current remains same across each resistance, not only for this chapter, any chapter when we are using this. AC chapter also you will be using. So current remains same across each resistor. So whatever the current which is flowing across this, I, same current will flow across this, I, same current will also be flowing across this. Next, current remains same. Potential difference, V, potential difference will be divided. That is, this potential difference will be divided as per the value of the resistance. So what is the equivalent resistance? Third one, the battery always watch equivalent resistance. So this will be R1 plus R2 plus R3. And if they are asking what is potential difference across this, that is V1. What is V1? I into R1. Across the resistor R2, what is potential difference? V2. What is V2? I into R2. And across this, across V3, and that is I into R3. Across the combination, always the potential difference will be given by, this will be R equivalent, and here the potential difference is given by V, and this one is R equivalent, current is I. So across the combination, we have the potential difference, and what is potential difference? V is equals to I into R equivalent, and what is R equivalent here? R1 plus R2 plus R3. Whatever the number of this resistance we have, just add it as it is. Next we have parallel combination. So if we talk about the parallel combination of the resistance, so when we talk about the parallel combination, one resistance this way, second resistance this way, third resistance this way, if they are considered in parallel combination, what we have to assume here is that, what we have to first point that here the current remains same, whatever potential difference remains same. Not only for resistor, for any things which is connected in parallel, they will be having same value of the potential difference for anything which is connected in parallel. So this will potential difference remain same across each resistor. Okay. Second, current will be divided. I will be divided. Yes or no? I will be divided as per the value of the resistance. So I will be divided. If I is dividing, how it will divide? Again, depends on the value of the resistance. I1, I2, this side I3 and this side I4. And what is R equivalent? 1 by R equivalent we can write here. This will be R1, this will be R2, R3, R4. So 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R4. So these are the R equivalent when they are connected in parallel combination. Remember this line. So this we are getting this 1 by R1 plus 1 by R2 plus 1 by R3. And what is potential difference? V1 is equals to V2 is equals to V3 is equals to V4 is equals to V. And what is V? I into R equivalent. What is I? Total current. And what is R equivalent? Total resistance. So here we'll be writing this V1. What is V1? I1 into R1. And what is V2? I2 into R2. What is V3? I3 into R3. And what is V4? I4 into R4. And what is I? What is I? Summation of all this, that is I is equals to I1 plus I2 plus I3 plus I4. Clear? Whatever the number of resistors I have mentioned over here, that many number of currents we have will be getting in parallel combination. So we'll be checking some of the questions on now. The two resistors are connected in parallel. The two resistors are connected in parallel. This one is R1 and this one is R2. If both are connected in parallel, we'll be writing this R equivalent. What is R equivalent? R1 R2 divided by R1 plus R2. Okay, R1 R2 divided by R1 plus R2, right? So this side, if you write this particular point, if resistance are connected in parallel combination like this, yeah. So this one, if they are connected in parallel combination like this, R, 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 how many times? N times. Then what is R equivalent? This will be R divided by N. If the resistance are connected in series combination, 1, 2, 3, 4, like that. So this one is R, this one is also R, this one is also how many times? N times. So what is R equivalent? Is equals to N into R. Yes, Sana, please continue this. Write the notes, everything. Write the notes. Next, a certain wire A has a resistance of 81 ohm. The resistance of another wire B of the same material, equal length, but diameter size is the diameter of the A. So R equals to rho L divided by A. So diameter of B is how many times? 3 times of diameter of A. Two wires are having A and B. The diameter of B is 3 times diameter of the A. So what is the area of the cross section? What is area of the cross section? Pi d by 2 whole square. That is we are getting here pi d square by 4. Resistance, I think they are having same material and equal length they have mentioned. Yes, they have mentioned equal length and same material. Resistivity depends on the material. 1 meter, 2 meter, 3 meter. All meter, whatever the meter of the copper wire will be having same value of the resistivity. So R equals to inversely proportional to area of the cross section. R is inversely to what is area? Pi d square by 4. That's it. Further calculation is R2 by R1. What we have to write? What we have to write? Certain wire A. So let's calculate this. I am calculating this. R of B by R of A is equals to D of A by D of B ka whole square. Right? D of B. That's it. So putting this, that is RB by 81 is equals to D of A. What is D of A? So this one is D, and what is D of B? 3D chi square. So how much you got this one? So RB value, that what we are getting here, this one is 81 by 3 chi square, that is 9. Answer is 9 ohm. Answer is option B. Okay. Next we have the combination of the resistor. When we talk about the combination of resistor, the resistance of the wire is R ohm. It is defined, melted and stretched to N times its original length. So there is one wire and length is R, length is L, and this is having area. So what is the volume? Volume equals to area into length right now. Okay. So what is resistance? Resistance is given by rho L divided by area. So this is the resistance of the wire we have right now. So R equals to rho L divided by A. Now what we are doing, we are melting this particular material of the wire. When we are melting this particular material of the wire and we are stretching it, so when we are increasing the length, area will decrease. This will become more thinner and thinner. Area will decrease. When the area will decrease, how much area will decrease? We don't know. That is what we are calculating now. So when the area will decrease, so what is area now? ADS. Let's check it. So area is ADS and length is how many times? N times the original length. What is length now? N multiplied by L. So what is the volume? Area into N into L. See, volume will not change on melting. Volume will not change on melting. Volume will be same. Volume of the material will not change. So area at ADS into N into L. This is equals to area into L. L or L cancel. What is ADS? We are getting A by N. So what is resistance? RDS. Rho L. How many times L? N times of L. Divided by what is area? A by N. So this will go upside. So RDS equals to N square rho L by A. So this particular term is again R. So what is RDS? Rho. What is RDS here? N square into R. So we are getting this N square multiplied R. Remember this, whenever on stretching or melting, if the length is becoming N times, then resistance will become N square times. Clear? A uniform metal wire of length L has 110 ohm resistance. What now the wire is stretched to 2L. Okay, fine. So initially, what is a L? Length is it is having certain length. What is resistance value? The resistance value is 10 ohm right now. Now the wire is stretched to length 2L. When we are stretching to length 2L, just now we saw that if you are stretching by N times, what is the resistance we are getting? N square into R. Now the length is stretched by how many times? The length is stretched to 2L and bend to form a perfect circle. So first, let's say, what is the radius now? What is the resistance now? This will be 2 square multiplied by original resistance. And what is this value? So 4 multiplied by 10. How much we got? 40 ohm. We got the answer as 40 ohm because it is stretched by 2 times. So resistance will become 4 times. Now what we are doing? We are not satisfied with this. What we are doing? We are bending it to form a circle like this. Okay. And what they are asking? Equivalent resistance across any arbitrary diameter of this. So this upper portion of this will be having some half of the resistance, and this lower portion of this will be also having some half of resistance. Now this resistance are connected in parallel combination. So this total is 40. So this upper portion will be how much? 20 ohm, and this lower portion will also be having 20 ohm. This one and this one are in parallel. So I can write here R equivalent equals to 20 by 2. Answer is 10. Clear? Answer will be option A. That is 10. 20 by 2. Two metal wires of identical dimension are connected in series if sigma and sigma 2 are the conductivity of the combination. Then, so here when we talk about this, they are connected in series combination. So you can note down this series combination. Direct form I am telling series combination. If you talk about the sigma effective, when we talk about the sigma effective for series combination, this will be 2 sigma C1 sigma 1 sigma 2 divided by sigma 1 plus sigma 2. If you have two different materials which is having sigma 1 sigma 2 as the conductivity. And what is rho effective? The rho effective we can write here rho 1 plus rho 2 by 2. Provided that they should be having identical dimensions. Whatever the formula I am telling, they should be having identical dimension. Then only we will be using this particular formula. Series combination 2 sigma C1 divided sigma 2 divided by sigma 1 plus sigma 2. Second is rho effective, that is rho 1 plus rho 2 by 2. So this one we will be writing this. Now if you talk about the parallel combination, so what is parallel combination? Resistance. Parallel combination sigma effective. So sigma effective parallel combination will be writing this. What is that? Sigma 1 plus sigma 2 by 2. And what is rho effective? Just reciprocal of this, just opposite of this, that is 2 rho 1 rho 2 divided by rho 1 plus rho 2. Rho 1 and rho 2 are respectively resistivity of the given conductors. Okay, so this is, remember this particular lines. The only condition is that conductivity they should be having same dimension. 10 resistors each of resistance are connected in series to a battery of EMF E and negligible internal resistance. So this they are connected in series 1, 2, 3 like that. How many resistance? 10 resistance. So total resistance will be how much? 10 R. And batteries EMF is E. Then those are connected in parallel to the same battery. The current increases n times. So what is I? I right now E divided by 10 R. Yes or no? Current is given by EMF divided by total resistance 10 R. Now in the second case, what is happening? Those resistors are connected in 1, 2, 3. How many times? Parallel. So this one is R, this one is R, this one is R, this one is R. How many times? N times. So what is R equivalent now? R by N, because they are connected in parallel combination. So what is the current now? The current now is given by, the battery remains same, E divided by what is R equivalent? Now here it was 10 R, now it is R by N. How many times? 10 times. So this will be R by 10. Okay. So because we are connecting 10 resistance in 10 times in parallel combination, this will become R by 10. So this will be R by 10 right now. So this will become how many times? R by 10. So this one is 10 E by R. Okay, 10 E by R. This value is I. This value is I. So whatever this value, so if we divide also, we'll be getting this. So 100 times of E divided by 10 R. So this is 100 multiplied by I, and they're asking N multiply I ka value. So what is N value from here? N value is 100. Answer is option A. Okay, answer will be option. Clear? So moving next particular question. This particular question is from the Kirchhoff's law, and we know that how to solve the Kirchhoff's law. We know that if we talk about this, the magnitude and direction of the current in the following circuit will be given by. So this 0.5 ampere from A to B. Let's talk about this. Will be this particular loop that I am writing here. Loop. What is loop? A, D, C, B. A again. So A to D, nothing is there, and let's say direction of current is, let's say, this way. The direction of current is, let's say, this way. This is what we are assuming, the direction of the current. Loop A, D, C, B, A. So in this case, A, D, C, B, A. A, D, C, B, A. We are moving opposite to direction of the current. So let's take direction. Current value is I. I value is flowing. We are moving opposite direction of current. We are moving D to C. So this will be plus 7 into I, right? Nothing is there. Again, we are moving opposite direction of the current, plus 1 into I. Next, negative of the battery to positive of the battery. This is negative of the battery to positive battery. This will become plus 5. And this side, positive of the battery to negative of the battery. This will be minus 10. Again, we are moving in this direction of the current across this resistance, opposite direction of the current. This will be plus 2I. This will be 0. Complete loop is there. This will be 0. So let's solve this particular case. 7 plus 1. This one is 2. 8 plus 2, 10. 10I minus 5 is equals to 0. So what is 10I? 5 by 10. So what is I value? 0.5 ampere, right? 0.5 ampere we are getting the values. What is direction of this? A to B. So whatever, when we are getting the value positive, remember this, whatever the direction that we assume, that is correct one. When we are getting the value positive, so if we are getting this particular value is positive, so whatever the direction that we assume, that is correct one. What is direction that we assume? A to B through E. Okay, answer is option A. Clear? Right. Okay, so when we are solving this particular case, that is, if the generator G shows no deflection, then in the circuit shown the value of the R should be given by. Okay, right. If it is showing no deflection, there is one simple trick to solve this. I can assume one particular point as 0 potential. So this will be 0 potential, this will be 0 potential, this will also be 0 potential over here. Okay, this will also be 0 potential. Now, what we have to find is that this will 0 potential 0. Whatever this one, this will be 2 volt. This one is 0, and let's say this one is how much? This will be 10 volt. Okay, that will be 10 volt. Now galvanometer shows no deflection. Here no deflection is there, so no current. Current value is 0. The current value is 0 means here we have 0 potential. This one is 2. Why 2? Because we are jumping the battery up 2 volt. So this side, if it is 0, this has to be 2 volt because difference should be 2 volt. So this one is 0 volt, this will be 2 volt. Again, this one is 0 volt, this one is 10 volt battery. So this has to be 10 volt because difference has to be 10. This side 10 positive and this side 0. So whatever this particular point, again this will be having potential difference of 2 volt over here. Now we got the potential difference. You got the potential difference here also. What is potential difference at this particular point? So potential difference is 10 minus 2. And what is potential difference is here? That is 2 minus 0. And the same current is flowing. So here I will be writing this 10 minus 2. Potential difference divided by resistance 400 should be equals to 2 minus 0 by R. Okay, 2 minus 0 by R. So from here we will be writing this 8 by 400 should be equals to 2 by R. So this is 1, this is 4 times. So what is R value? 100 ohm. So from here we got 100 ohm is the answer. That is R value 100. So this particular question, that is Kirchhoff's law for open circuit. So this point is A and that point is B. We are going, this is for open circuit. Don't put delta V as a 0 because this is open circuit. So in that case we will be writing this always start with journey, that is we starting from point A, we are going from A to B. Okay, no confusion, we should be going from A to B. Okay, and what is that? We'll be writing this VB minus VA always. Final potential minus initial potential. When we are moving in the direction of the current across resistance, we have to take it as negative. So this side minus 2 into resistance 2. Positive to negative we are going. Again we have to write minus positive to negative we are going. Again the direction of the current is same. So this will be minus how much? What is current value? 2 ampere. So this will be 2 into 1. So this is what we are getting the values. So what is VB minus VA? That's it. So what is VB minus VA? We are getting this minus 4, minus 3, minus 2. We got minus 9 volt. But they are asking VA minus VB. If VB minus VA is this minus 9, so this will be plus 9 volt. Answer is option D. I hope this one is clear. VB minus VA we have to take only final minus initial and don't take to be 0 because this one is open circuit. Kirchhoff's law for open circuit. Across the resistance minus I into R because current is flowing like this, and across the battery plus to negative, again this will be minus. So next we have this EMF internal resistance and combination of the cells. So for example, if we have the batteries connected like this in this particular case and resistance is across this way. So two things are there when we are going to purchase the battery in the market. Whatever the quoted potential difference across the battery, that is the terminal potential difference. Whatever the quoted, what is the rated potential difference, that is a terminal, that is the EMF, electromotive force. What is potential difference? When we are connecting this particular battery with external resistance R, then current will start flowing through this. In that case, whatever the value will be getting across the, whatever the terminal potential difference will be getting, that is a actual terminal potential difference we can see. So here we will be writing this V is equals to E when cell is open. Okay, when the cell is open, potential difference across the terminals of the battery, will be writing this when the cell is open, that is V equals to E. And when the cell is closed, if the cell is closed like this, so this one is closed, V is equals to E minus I into R, and I is the current that is flowing through the given circuit, R is the resistance. Okay, R is the internal resistance of this cell. So here certain things that we can write here, I is equals to net EMF, always remember this, net EMF divided by R total resistance. So I is equals to net EMF E divided by R total, R plus small r. This one is first one. Second is V is equals to I into R. Whatever the current which is flowing across this, we can use this particular formula also. Third particular formula that we will be using, R is equals to capital R into E by V minus 1. And this one V equals to E minus IR. This one is, if we talk about this, these are the formulas we have for the cells and potential difference and the internal resistance of the battery. Suppose if the battery cells are connected in series combination. So remember this, cells in series combination. So when we connect series combination like this, positive, negative, positive, negative, positive, negative, positive, negative. If they are connected in series combination like this, it is connected to this. This one is having E1, E2, E3, and this will be E4. So what is the net resistance? Net equivalent resistance will be writing this. E net will be writing this E1 plus E2 plus E3 plus E4. If they are connected properly like this. And what is R equivalent? What is R equivalent? This will be R1 plus R2 plus R3 plus R4. And what is I in the given circuit? Net EMF divided by R total. E net divided by R total. What is R total? External resistance plus internal resistance, that is R equivalent. So this is R equivalent. This is the I that is flowing to given circuit. And if they are asking V1, that is potential difference across battery 1. So what is V1? E1 minus I into R1. What is V2? E2 minus I into R2. What is V3? E3 minus I into R3, and so on. Like this it will keep on increasing. Like that we'll be writing for different potential difference across this battery V1, across this battery V2, and across this battery V3, and across this battery V4. So this is what net current in the circuit. As the cells are connected in series combination, current will be same across each battery as well as resistance, as well as internal resistance, external resistance as well. Potential difference has to be divided because they are connected in series combination. Second, in this case, suppose that the cells are connected like this, positive, negative, but negative and positive is connected. Okay, so negative and positive is connected. In that case, we have to check it. What will happen? The negative and positive is connected again. Positive and negative is connected like this, and this is connected to external resistance capital R. So this one is having E1, R1. This will be R2. This will be E2, and this will be E3, and this is R3. So which is breaking the order? Which is breaking the discipline? So this one is E1. but this one is minus plus E3. So this one is net EMF. And what is R equivalent? R equivalent is 1 by resistance will be added as it is, R1 plus R2 plus R3. So this thing that we should keep in mind. This is the cells in series combination. Suppose if you write cells in parallel combination as well. Cells in parallel combination. So cells in parallel combination, if you're writing this, one cell like this way, second cell like this, third cell like this if it is connected, this one E1, R1, E2, R2, and third one is E3, R3. And it is connected like this to external resistance capital R. In that case, what will be writing here? E net will be writing this E1 by R1 plus E2 by R2 plus E3 by R3 divided by 1 by R1 plus 1 by R2 plus 1 by R3. So this is cells in parallel combination. Okay, net EMF in parallel combination. And what is R equivalent? That is all are connected in parallel, 1 by R1 plus 1 by R2 plus 1 by R3. So this is the R. Now this R equivalent and this resistance external resistance will always been connected in series combination. Remember this. This one, this all parallel combination, this one will be in series. So let's see some of the questions from here as well. That is the. So student, measure the terminal potential difference of a cell. Internal resistance R is a function of the current flowing through it. The slope and intercept a graph between the V and I respectively. So here the graph is V versus I, and we know that V is equals to E minus IR. If I compare this, this is Y and this one is C plus MX. So along X, what we are plotting? Along X we are plotting the I. Along Y, what we are plotting? We are plotting the V. Comparing this to equation, what is M? M is minus R. Comparing this to equation. And what is C? C is E. Internal resistance, Y intercept, the graph is like this. So this particular point, that is EMF E, and this particular point, we don't know, this particular point voltage is 0. So what is the slope? The slope will give us minus R. So here the intercept, what is that? The slope and intercept, the graph between, the slope is minus R and Y intercept is E. Okay, slope is minus R. Compare this, V equals to E minus IR. Right. The terminal voltage of the battery whose EMF is 10 volt and internal resistance is 1 ohm when connected through external resistance of 4 ohm is given by this. So they're asking potential difference of this. What is, first we have to find what is current in the given circuit. What is current in the given circuit? I is equals to E divided by R plus small r. Total potential, that is 10 divided by resistance, that is 4 plus 1. How much they're asking? That is 10 by 5. We got how much? 2 ampere. 2 ampere is current flowing across this. Okay, 2 ampere is current which is flowing across this. So what is V? E minus I into R. So 10 minus I, 2 into what is R? 1. What is answer? 8 volt is the correct answer over here. Okay, 8 will be correct answer over here. Right. So next topic is electrical energy and power. So what is electrical energy? Joule's law of heating says that H is equals to I square RT for any resistance. If current is flowing here I, resistance is R, and current flows to given time T, till time T current is flowing. So heat that is heat across this resistance given by H equals to I square RT, where I is the current, R is the resistance, T is the time. This is the heat energy. Heat energy is equivalent to electrical energy. And if you talk about the power, what is power? Power is energy divided by time. So this side I square RT divided by T, T or T cancel. So what is the power? Power is I square into R. So let's discuss this power. So if we talk about this resistance over here, current that is flowing here I, resistance is R, then power is defined as I square into R. In terms of the current, that is current flowing through the given resistance is I, resistance is R, power across resistance given by I square multiplied by R. In terms of the potential difference, we should be knowing what is the potential difference across the 2 points. So this particular point A and this particular point B, we should be knowing the potential difference. So here potential difference is, let's say, V, and resistance is R. The power is given by V squared divided by R. Okay, the power is defined by V squared divided by R. So this is the power condition. When to use this one, when to use this one. When the current is given, resistance is given, you have to use this one. And the voltage difference across the resistance of this given, we have to use this one, that is V squared by R. So let's check some more things in this. That is the electrical energy and power. What is rating of the bulb if you talk about? So any bulb, suppose if it is rated like this, the bulb is rated like 40 watt and 220 volt. It means that bulb will glow with a 220 bulb will glow with a 40 watt at a voltage of 220 volt. If you give more voltage, the bulb will fuse. If you give less voltage, the bulb will glow with less power. So maximum power it can have is 40 watt, and maximum voltage it can withstand is 220 volt. It can't withstand more. It is more than that, it will fuse. So from here, whenever this rating is given, we'll be always calculating. This is we defined it maximum power rating, and this is what we define maximum voltage rating. So here we define resistance. We can calculate from here, from this particular formula, V max squared divided by P max. What is P? V square by R. From P equals V square by R. From that we are getting this R equals to V max divided by P max. So let's talk about this series combination of the bulb. So let's say I have a 3 bulb. Okay, I have 3 bulb. First bulb, second bulb, and third bulb. All are rated 220 volt. So this one is also 220 volt. This one is also 220 volt, and this one is also 220 volt. But first one is having power of P1, power rating of, let's say this one is having power rating of P1, 220 volt P1. This is 220 of P2, and this 220 volt P3. When we are connecting this, and remember this, whatever the source voltage that we are connecting, that should also be having 220 volt if all the bulbs are having power rating of voltage rating of 220 volt. So when we are connecting this and this one, P1, P2, P3, in that case, the power equivalent power is given by this particular relation, that is 1 by P equivalent is given by 1 by P1 plus 1 by P2 plus 1 by P3. Again, what is condition for this? They should be having same voltage rating, okay, and they should be having connected to same voltage rating. Then power equivalent will be given by this 1 by P equivalent equals to 1 by P1 plus 1 by P2 plus 1 by P3. Parallel combination, again, this not only apply for the this not only for the bulb, for any other cases also will be applying this. So 1, 2, and third one. Again, both are having same power, or both are having same voltage rating. P1 220 volt. This one is having P2 220 volt, and this one is having P3 220 volt, and this voltage is 220 volt. In this case, parallel combination, we'll be writing this P equivalent is given by P1 plus P2 plus P3. The power will be added in parallel combination like this, provided that all the voltage ratings should be same, P1 plus P2 plus P3, and here 1 by P1 plus 1 by P2 plus 1 by P3. So this concept we can use in different form, different questions we can use. The only condition that I already told you. So let's see some of the questions from this power as well. So 1 by P equivalent, 1 by P1 plus 1 by P2 plus 1 by P3, this one is. So let's see. Two heaters A and B have the power rating of 1 kilowatt and 2 kilowatt respectively. Those two are connected in series first. So heater 1, okay. Heater is also resistor. So this heater 1 and heater 2. This having power 1 kilowatt and this having power 2 kilowatt. Voltage rating is same, let's say. I am giving, let's say, 220 volt, and this is also 220 volt, which we have domestic electric supply, right? And let's say it is connected to again 220 volt rating only, that is 220 volt power supply only. Those are the first connected in series and then in parallel to a fixed power source, right? Now in the second case, what is the power you can calculate from here? 1 by P equivalent, and what is that? 1 by 1. Just now we got, no? What is the power in series combination? 1 by P1 plus 1 by P2 plus 1 by P3. The same fixed power source, right? This 1 by P1 plus 1 by P2. What is this? 1 by 1 plus 1 by 2. How much we got? This is 1 plus 3 by 2. So equivalent power that we are getting here, that is 2 by 3 kilowatt here in this case. When they are connected in parallel combination, the heater like this, one heater this way and second heater this way. It is connected again 220 volt. So this one is having power 1 kilowatt and this one is having power 2 kilowatt. So what is equivalent power? 1 kilowatt plus 2 kilowatt, because they are connected now in which combination? Series parallel combination. So power will be added. So what is the equivalent power in the both the case? This is power equivalent in series. So 2 by 3 divided by 3. How much you got? Answer is 2 by 9. Okay. So this will be 2 by 9. Two resistors of the resistance 100 ohm and 200 ohm are connected in parallel in electrical circuit. The ratio of thermal energy developed in 100 to 200. So one resistance this one and second resistance this one. Okay, they are connected in parallel in electrical circuit. The ratio of the thermal energy developed in 100 to 200 ohm will be given by. So this, let's say it is connected to voltage source V, and both are connected in parallel combination. So with this one and this one will be having same potential difference, because I told you in parallel combination they will be having same potential difference. So this I'll be writing this P1. What is P1? What is P1? What is P1? P1 is given by V squared divided by R1. Okay, and second is this side P2. What is P2? V squared divided by R2. Again, this across this resistance, the voltage will be same. So first one is having resistance of 100 ohm and second is having resistance of 200 ohm. The voltage will be same across both because they are connected in parallel combination. Okay, they are connected in parallel combination. This will be 200 ohm. So we'll be writing this, the power combination. So P equivalent is equal to this side. P equivalent will be this side. Now they're asking the ratio of this. So what is ratio? P1 by P2. What is P1 by P2? If you divide this, this will become R2 by R1. Okay, R2 by R1. So R2 value will be getting this 200 divided by 100. So answer is 2 raised to 1. So obviously the power will be more across this resistance over here. Okay, V square by R1, second is V square by R2. Right. So answer is 2 raised to 1. A filament bulb 500 watt 100 volt. So this in the filament bulb 100 volt means maximum voltage rating it can have 100 volt and the maximum power rating it can have 500 watt. Means if you give more than 100 volt it will fuse. But what is the problem? It is to be used in 230 volt main supply. So here we have main supply voltage of 230 volt. So this one is 230 volt supply voltage and there is one bulb is connected like this. Okay. So in that case, what we have to do, if I directly connect this bulb with this, the voltage rating is 230 volt and this is having 100 volts. So if I directly connect it, obviously this bulb will fuse. So for that purpose, what we are doing, one resistance R is connected across that. We are connecting one resistance R across that so that it works perfectly fine and bulb consume 500 watt. Means maximum voltage that it is consuming here is 100 volt. Remember this. So what is remaining? Out of 230, 100 is going here. So out of 230, 100 is going here. This side how much will be? 130. Okay, and we can calculate this. What is the power of the bulb? Power of the bulb is 500 watt. So we want to calculate. So there is one more formula for the power. Power is V multiplied by I. What is power of the bulb? 500 is equals to voltage is equals to 100 multiplied by current. So what is current value we are getting here? Current value, that is 5 ampere is flowing. Now 5 ampere is flowing across this bulb. We got P is equals to into I. The same 5 ampere current will be flowing across this resistance as well. And from this, if I write from this Ohm's law, V is equals to I into R. So what is V value? 130. And what is I value? 5 multiplied by R. From that you got the answer, that is 130 by 5. Answer is how much? 26 ohm. So this resistance should be 26 ohm. Six similar bulbs are connected as shown in the figure with DC source of EMF E and 0 internal resistance. So like that. So this is DC source of EMF E and 0 internal resistance. Now, so they are having 6 similar bulbs, means all are having same resistance R, 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 R. They all are having same resistance. Okay. The ratio of the power consumption by the bulb when all are glowing. Okay. When all are glowing, the first case when all are glowing means all are there in the given circuit. So when this one, these two resistance. So if I draw this, one resistance, two resistance, and this will be 3 resistance. So in this case, this is connected to the voltage source like this. So this one is R, 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 R. So we are getting this how much? 2R, 2R, 2R. All are connected in parallel. So this will be, so one is 2R and second is also 2R and third is also 2R. They are all are connected in parallel combination. So we can write directly here. This will be R by 2R by 3 and this will be EMF. And what is the power across this? The power across this will be writing this potential difference is E only, right? So this will be E square divided by 2R by 3, right? E square divided by 2R by 3. This is the first case when all are glowing, right? Next, in the switches when the 2 from section A and 1 from section B is glowing. 2 from section A, 2 from section A and 1 from section B is glowing. So in this case, 2 resistance from the left side and 1 resistance from the right side that will be taking. Resistance again R. So this will be R, this will also be R. So what is the combination of this? So this one parallel combination R and R, R by 2, R by 2 plus R, 3R. So in this case, this will be R by 2 plus R, that is 3R by 2. So this, we'll be writing this. What is power in the second case? E square divided by 3R by 2. So this is power P2. That's it. Power P1, E square divided by 2R by 3. So we have to take the ratio of this two. That's it. So this we got 3 by 2, E square by R. And this one we got 2 by 3. 2 by 3 E square by R. And this one we got 3 by 2 E square by R. So P1 by P2 is equals to 3 by 2 divided by 2 by 3. So 3 3 is a 9 by 4. Answer is option, which option? 9 raised to 4. Clear? So this is what we are getting, the ratio of the power in two different cases. We just now see the parallel combination for both the bulbs over here. Next one we have this a small topic, that is the Wheatstone bridge. What happens in Wheatstone bridge? This resistance by this resistance should be equal to this resistance by this resistance if the bridge is balanced. So in a network of the 4 resistance or 5 resistance, we can connect the battery is connected between the middle of the 2 resistance like this, and galvanometer is connected between these two resistance over here. The galvanometer shows no deflection. G shows no deflection means no current is flowing. No deflection, no current is flowing. In that case, no current is flowing. In that case, what will you writing? If no current is flowing across that, for that we can write here P by Q is equals to X by Y. So what is that? This resistance by this resistance should be equals to that resistance by this resistance. Across this we have to check this between this. P by Q should be equals to X by Y. So this is what we call arms. This arm by this arm, that is P by Q should be equals to X by Y. So when this condition is satisfied, this happens. Current does not flow across the galvanometer. Now, for the most precise accurate measurement of X, the resistance P and Q should be given by. Resistance P and Q should be, whenever we compare the things, they should be almost equal to each other. Whenever we are comparing the things, in real life also if we are comparing the things, they should be equal to each other. So P and Q should be approximately equal and are small. In that case, it will be more sensitive. If it is they are not equal, then also reading will be there. Then also it will work, but it will more efficiently work when they are having equal resistance and approximately small resistance, right? So resistance of the 4 arms of P, Q, R, and S in the Wheatstone bridge. So one is P and second is like this. Here we have, so this side we are continuing like this. So resistance of the 4 arms, this one is P, Q, R. So this one is having how much? 10 ohm as per the given question. This one is also having how much? 30 ohm. This one is having again 30 ohm, and this one is having 90 ohm. The EMF and the intensity of the cell are 7 volt and 5 ohm respectively. The galvanometer is having resistance of 50 ohm. The current drawn from the cell should be given by, they have given the internal resistance as right. So in this case, let's check this whether this condition is satisfied. This by this should be equal to that by that. Let's check this. 10 by 30 should be equal to 30 by 90. Yes, we are getting. So this condition is satisfied means no current flows through this galvanometer. Current does not flow here. So no current flows through galvanometer. So no need to consider the resistance of the galvanometer. So in this, no current flows through G. In that case, we don't have to consider the resistance of the galvanometer. Just now, as it is, whatever we have here, we have these two are in series combination. If we go like this, these two are in series combination. This one is 10 ohm, this one is 30 ohm. Again, these two are in also series combination. So this 10 ohm, 30 ohm. So total will be on this side we are having 10 plus 30, and these two are also in series combination. This one is how much? 30 plus 90. Together they are connected in parallel combination, and we can find the current and resistance small r. So this one is 40 and this one is 120. So what is R equivalent? I am writing here directly. That is 40 multiplied by 120 divided by 40 plus 120. So this we are getting 120 divided by 1 plus 3, So we are getting this 120 divided by 1 plus 3, 120 divided by 4, answer is 30. So this is 30 ohm, right? And here we are connected, this is connected to the what is battery potential difference, that is EMF is 7 volt, and what is internal resistance? It is connected to this. So this one is 7 volt, and what is internal resistance of this internal resistance? So this one is 7 volt. So this will be 7 volt. What is internal resistance we have? 5 ohm. Now this one and this one, remember this always. The external resistance and internal resistance will always be connected in parallel. Oh, sorry, in series, because it is in a single loop. So what is I? Net resistance. Sorry, net EMF. Net EMF by total resistance. So what is net EMF? We have total, that is 7 by total resistance, that is 30 plus 5. So we got this 7 by 35, 0.2. Answer is option D, 0.2 ampere. Okay, 0.2 ampere. Next we have this particular question over here. The given circuit shows a uniform, this is the meter bridge. And what is a meter bridge? Meter bridge is the application of the Wheatstone bridge. So Wheatstone bridge will be having two jaws, this side one resistance, this side also one resistance, this side one resistance, this side also one resistance, like that. So this particular setup we can consider in terms of the Wheatstone bridge, where this portion of the wire will be having some resistance and other portion of the wire will be having some another resistance. So what actually happens in the meter bridge? We are using this particular principle, R is proportional to length. More is the length of the wire, more will be resistance of the resistance of that wire, right? So here let's talk about this particular question. So for example, let's give little bit idea about this. So this one is having 8. So this particular portion where it is giving, this particular portion of the wire will be having some resistance R1, and this particular portion will be having some resistance R2. So here we'll be writing this. Always remember this. It is condition of Wheatstone bridge. This resistance by that 8 by R1 should be equals to 12 by R2. Now I told you R is proportional to length, right? So this length is L1 and this length is L2. Okay, so I can write here, from here I can write 8 by 12 is equals to R1 by R2. So R is equal to L. So what is this? R1 by R2. What will be writing R1 by R2? L1 by L2. So from here we can write that is L1 by L2. Okay, right. So the given circuit shows a uniform straight AB of the 40 centimeter fixed, and again this total length between A and B is nothing but 100 centimeter. Remember this. Most of the time it will be 100 centimeter, unless they have specified in the questions. We have to take this one as 100 centimeter. So this total length is 100 centimeter. 40 AB of 40 centimeter length fixed at both ends. So right now in this question they have mentioned this one is 40 centimeter. Okay, so this distance is 40 centimeter. In order to get zero reading in the galvanometer, so when this condition is satisfied, the balance condition of Wheatstone bridge, so this is equivalent to Wheatstone bridge obviously. So in this case there is no current that is flowing across this galvanometer, current is not flowing across this. So this resistance by that we have seen by this resistance by this. So in that case here no current is flown. The free end of J is to be placed from B at how much distance? So this L2 they are asking. Okay, they are asking L2 distance over here. So we not got the relation. What is the relation we got from the calculation? That is 8 by 12 is equals to R1 by R2 is equals to L1 by L2. Okay, so from here we can write L1 by L2 is how many times? 2 by 3. So what is L1 by L2 is 2 by 3. This is one equation we can write here, that is L1. If I write L1 equals to 2x, it will not be wrong. If I L2 write L2 equals to 3x. Second is, what is total length between A and B? A and B, what is total length? They have mentioned the question is 40 centimeter. So this L1 plus L2 is equals to 40 centimeter. Putting the values here, 2x plus 3x equals to 40 centimeter. So 5x is equals to 40 centimeter. Then what is x? 8 centimeter. Then what is 3x? 3 into 8, because they are asking L2. So this will be 24 centimeter. Answer is 24 centimeter. What is 2x? This one is 2 into, this is 16 centimeter. So this will be 16 centimeter. If they are asking distance of this particular point from A, that is 16, and this will be 24. I hope this is clear to everyone. So for today, that we cover some of the concept from this total, from different concept that we have covered, from the starting from the current, what is current, average current, instantaneous current. Then we have different terms. You can go and revise all of those formulas: resistivity, current density, drift velocity. Then also we discuss the combination of the resistance. Series combination, current will be same across each resistor. Parallel combination, current will be divided but potential difference will remain same. And Kirchhoff's law also we discussed. Some of the rules were discussed. We are moving in the direction of the current across the resistor, opposite direction of the current across the resistors. We got the values. Electrical power, you might be getting confusion from the electrical power. So electrical power, remember this, we have certain formulas that P is equals to V into I, P is equals to I square into R. Depending on the situation, what the value they are given. If the current is given, put I square into R. If the potential difference is given, V square by R. So these are the for the today. Tomorrow we'll be coming with the chapter that is the moving charges and magnetism, and some of the questions, some of the topics from the bar magnet as well. So tomorrow we'll discuss what is Biot-Savart law. We'll be using the different Biot-Savart law and Ampere-Savart law. Then also we have the force and torque on the moving charge and coil. So again, tomorrow's chapter, weightage wise, it is good weightage. So please do attend and keep practicing till keep revising. All the best.